he is responsible for making a lot of new sophisticated AI models available in Keras. And Ryan Gillard is an AI engineer at Google Cloud. He's part of Google Cloud's professional services organization, has been working with a lot of Google Cloud customers to help them implement models. Like the most recent customer that Ryan's been working with is Mayo Clinic. Next slide, Martin. And you can always reach out to us with questions on Twitter. I'll start off by basically talking about what's in the book, and then we will present 3 topics from the book. First, Martin will go and talk about a specific ML model for vision, and he's going to pick object detection models, RetinaNet. And then Ryan will talk about GANs, and then image generation. And then I will talk about a computer vision use case, which is of image search. And then we will basically do an overall Q&A. But in between our sessions, if you have specific questions about the technical topic that we just talked about, go ahead and just put that question in the chat, and we will answer it between our sessions. Next slide. So basically, the book starts off by looking at the kinds of things that you want to do with machine learning for computer vision. As you know, images and doing deep learning on images is pretty much like a hello world. It's the thing that we learn whenever we learn about deep learning. So we basically start with how about we take a deep neural network and neural network with multiple layers, and we implement it with Keras. And we basically read in an image, and we try to do image classification on it. And we show that it doesn't work all that well, right? A fully connected deep neural net on a moderately sized data set, we use a flowers data set as our example, doesn't really work. So next slide. So why doesn't it work? Well, it doesn't work because it doesn't take advantage of spatial correlation. So there are a few things that we could do. First of all, for example, we can go ahead and use pre-trained models, right? We can basically take an already trained model like EfficientNet or ResNet or MobileNet, and then basically keep most of the weights of that model the same, and then just train the last layer. So that's called transfer learning. The other thing that we could do is we could actually go ahead and change all of the weights of the model. That's called fine-tuning. And we have to basically set up a learning schedule in place. So we talk about the easy thing to do, which is to use a pre-trained model and adapt it for your data set. But then, next click, we start to go ahead and look at other things that we could do, right? We started to look at how to take advantage of spatial correlation. Next click, Martin. Oh, it moves to the next slide. Okay, sorry. Okay, let's go back. Okay, good. Okay, so it looks at different different tricks, right? So how to basically use correlation, how to use short circuit layers, how to basically do depth separable convolutions, and then like how to optimize for different things, such as you want low power or you want low memory. So you basically have different families of ML models. And then finally, we then say, okay, now you have a use case. You have all of these different model architectures. How do you choose between them? And having done that, we then take these things, which we will call backbone architectures. And we say, once you have a backbone architecture, how do you use it for other things other than image classification? How do you use it for object detection? How do you use it for image segmentation? And when you talk about image segmentation, you have 2 types of segmentation. You have instance segmentation, where you're trying to find objects, and semantic segmentation, where you're trying to find like all of the trees in an image, for example. Next slide. Okay. And then we move on to talking about how to build a production model. So chapters 5 to 10 are about all of the steps to go ahead and build a production model, from creating your data set in chapter 5 to different types of pre-processing and data augmentation in chapter 6, to how to do model training in a resilient way in chapter 7, in a distributed way, taking advantage of GPUs, etc., and how to do that, how to max out your use of GPUs. And then we then look at how to deploy your model in chapter 8. And then in chapter 9, we talk about how to use that model in order to get predictions in a different types of scenarios: online predictions, batch predictions, streaming predictions, etc. Right? So once we do that, we now take this entire pipeline, both training pipelines and prediction pipelines, and we show how to put them into a pipelines framework, right? A Kubeflow pipelines, and then productionize them. Next slide. Okay. And finally, we end the book in chapter 11 and 12, looking at advanced vision problems like image generation and text generation. Next slide. And so now let's switch over to Martin, where he will basically talk about one of the topics in the book, which is on object detection.
Hello, everyone. Thank you, Lak. So I'm Martin. And one of the things that we have tried to do in this book is to give you the keys to understanding how these vision neural networks work. What are the pieces, how they are assembled. And the end goal is that when you, not necessarily that you reprogram them yourself, but when you take one of those models out of a library of models, like for example, TensorFlow Model Garden, you know what the parameters are and how to tinker with them and how basically to adapt them to your own data. So let's have a look at a classic in object detection, which is called RetinaNet. Object detection is about spotting objects, putting a frame, a box around objects in an image, and identifying what those objects are. So for example, here, butterflies. How does this work? So first, we feed the image through a convolutional neural network, just as for classification. The convolutional neural network transforms the image into what we call feature maps. And as the image flows through the entire convolutional stack, you have many intermediate feature maps from which to choose from, and from which we could then start computing the bounding boxes and the classes. The question is, which one do we tap into? A feature map from the beginning of the neural network? Those ones are typically high resolution. So it sounds like a good choice if you are detecting small objects and want to detect them with some precision. Or a feature map from the end of the convolutional backbone. And those typically have good semantic information, because the way these convolutional backbones transform images is that they filter them and they distill semantic information as they go. So the first convolutional layers will identify very low-level semantic features like edges, corners, textures, and so on. As the image flows through the convolutional backbone, then the small-level semantic features will be assembled into bigger semantic features. For instance, here, if we are looking at flowers, those would be petals and leaves and stems. And then towards the end of the backbone, those features in turn get assembled into what you are trying to detect. So here, for example, a flower. So tapping into the feature maps, what I call the feature maps are the blue boxes here on the screen, which represent numbers. Those are arrays of numbers. Tapping into feature maps from the end gives you good semantic information. But it looks like you want both, doesn't it? So various approaches have been taken. Historically, here are three of them. YOLO, the YOLO architecture is one of the earliest object detection architectures, one of the fastest as well, and it just uses the lost feature map from the convolutional backbone. There is good semantic information there, So the object recognition part, identifying that this is a flower or a butterfly and so on, works very well. The positioning is a bit coarse. In the middle, you have another classic SSD, single shot detector. This one chose to use a couple of the feature maps from the end of the convolutional backbone. But really, what you want is to have the best of both worlds. You want both good semantic information and good localization precision. And that is why feature pyramid networks were invented. The basic idea is that you want to mix in some of the good semantic information from the end of your backbone into all of the feature maps at the different resolution levels that are of interest to you. So let's see in more detail how an FPN works. What you see here is a very schematic representation. This is the full picture. On the left, the convolutional backbones, and here I selected 3 levels in the backbone to extract information from. So we start with 3 feature maps at 3 resolution levels in the backbone. Now, the goal is to take the last one and to somehow add it into the rest, but they don't have the same shape, so you can't just add them. Never mind, we know how to change the shape of a cube of data. 1x1, 1x1 convolutions can be used to change the number of channels, which is the height here of the cubes of data. And we adapt all of them to have 256 channels. And then if they have different X and Y resolutions, it's easy enough to upsample them. Simple nearest neighbor upsampling, as if you were zooming in an image. And now they have the same X and Y resolution, the same number of channels. We can add them together. Those are the plus signs in the image here. And you get at the end, the blue boxes, which are feature maps at various resolution levels, which all have mixed in the good semantic information from the end of the backbone. So those feature maps will be good material for us to extract position and semantic information for object detection. That's what we will use. And so the end result here is that you have at each one of those levels, you have good semantic information for classification, but you can also tap in the appropriate level for the kind of size of objects that you want to detect. So typically the top levels, the feature map with the best spatial resolution will be good at for detecting small objects that you need to localize precisely, while the one at the bottom, which is relatively low resolution, will be good at detecting large objects that span almost the entire image. Now, how does this work in practice? How do you create a bounding box from these numbers? So here, let us focus on one feature map. That's the cube at the bottom here. It's a cube of numbers. And I would like you to focus on one column of numbers in this cube. It's highlighted here in red. Each column in this feature map corresponds to a physical location, XY position, in the image that was fed through this convolutional backbone. So those positions corresponding to the columns in the feature map are represented here as yellow dots. Now, it would be fairly easy to take each column of data from the feature map and transform it to obtain a bounding box. That works. It's vector to vector. A bounding box is simply x, y, and width and height. It's 4 numbers. But we have one technicality to work around, which is that neural networks are typically good at predicting small numbers around 0. And a bounding box is not made of small numbers. It has a position, XY position in a large image. It can be in the hundreds or thousands in pixels. And neural networks are good at predicting small numbers around 0 because neural networks use nonlinear activation functions like the sigmoid or the ReLU, and those are typically nonlinear around 0. So it's around 0 that they have good discriminating power and they can create interesting things. So how do we mathematically transform our problem to make it a problem of predicting small values around 0? So the trick here is to hard code pre-made bounding boxes that are centered around each of those locations in the image that correspond to a column of data in the feature map. And then the bounding boxes that each one of these columns of data will predict will be encoded relatively to these so-called anchor bounding box that we hard-coded in the image initially. So only small deltas, small variations of position and size. And those small variations are numbers around 0. Of course, we have to make sure that the anchor boxes have a wide variety of sizes and aspect ratios so as to cater to all possible cases of large objects, small objects, elongated objects, compact objects, and so on. So typically in the retina-net architecture, we use 9 different anchor boxes at each location in the image. And you can see them here on the right. So now that we define the problem like this, it becomes a fairly easy problem. A problem of taking one column of data, one vector of data from a feature map and feeding it through some transformation that transforms it into another vector of data, this time for the detection head, a vector that corresponds to x, y, or rather delta x, delta y, delta width, delta height, so a predicted bounding box relatively to one of those 9 anchor boxes. And there is a corresponding classification head that also takes that column of data from the feature map and outputs class probabilities to recognize what object this is, whether it's a butterfly, a rose, or whatever else. The last problem we have to tackle is, well, now the network is predicting boxes and classes. But how do we know that it's the right boxes and classes? So let me come back to the previous picture here with the anchors spread around on the image. Again, imagine that the image is covered in a sea of pre-encoded anchors. You have 9 anchors for every yellow dot, which corresponds to a position in the feature map. So that's a lot. And now imagine that you know what the correct box is because you have training data. So you know the ground truth. Imagine you drop one ground truth box on top of this image, on this sea of anchor boxes. How do you know which anchor box is the one that will correspond, that will predict, that will be trained to predict an object corresponding to the ground truth? Well, you simply intersect them and select the one that has the best overlap. So in the end, you have your anchor boxes, you drop one ground truth box on them, look for the best overlap, select one of the anchor boxes, and then you will encode a loss function that will say, that anchor box that I have selected that has the maximum overlap with my ground truth, that one is now supposed to predict that there is an object here, let's say a butterfly here. All the other anchor boxes are now supposed to predict there is nothing. We call that the background class. They see only background. And now you have what you need to build your loss function. So let's put all of that together. Here is the full RetinaNet architecture. On the left, again, we start with the backbone. Here, it's a ResNet 50 backbone that has actually in the RetinaNet architecture, they extended with 2 additional layers to compute even lower resolution feature maps, which are useful for detecting very large objects. Then the next stage is to, as I said previously, mix in the good semantic information from the bottom of this backbone into all of the other levels. And in the RetinaNet architecture, you typically select 5 levels through your backbone at which you extract feature maps. So then you mix in the good semantic information from the last level throughout your selected feature maps in the feature pyramid network. And you obtain the feature maps, which are now good material for detection and classification. So then you feed each one of them through a detection head and a classification head. And as explained previously, the problem of generating detections and classifications now is encoded as a simple problem of transforming one vector, one column of data from one of those feature maps into another vector, either a set of class probabilities for the classification head or a set of coordinate deltas for the bounding box head. So simple, you see here the design of the classification and detection heads. It's a simple sequence of convolutional layers. And that's the full picture. Now, for those of you who are used a little bit to neural networks, when I explained how you select, how you compute the loss for this neural network. You remember I said that you drop a ground truth box on this sea of anchor boxes, take the maximum, take the maximum overlap, and then train that anchor box, that one selected anchor box that has the max overlap with the ground truth box, train that one to detect an object and all the other ones to detect the background. Well, across all of the 5 levels in the feature pyramid network, and with all the anchor boxes we have here, in a typical RetinaNet architecture, you will be working with something like 100,000 different anchor boxes. And when you hear a problem like 100,000 anchor boxes are now supposed to see nothing, the background, and one of them or a couple of them are supposed to see an object, immediately you should have alarm bells ringing in your head saying, no, this is a case of extreme imbalance. You will be adding losses, so small errors produced by all of those predictions, and 100,000 of them are going to predict background. So something like an object probability close to 0. And you'll be adding contributions from all of them, and only a handful will be predicting an object, so an object probability close to 1. If you just sum up the contributions from all those predictions into one giant loss, you will have a case where the background predictions will drown out the useful signal from the couple of boxes that are supposed to be predicting an object. So RetinaNet actually has a mathematical tweak on the loss function they use to overcome that. Normally, when you do classification, in this case, let's simplify this to a binary classification problem, object versus background, you use the binary cross entropy loss. So that's the blue dotted line curve that you see here on the graph. And you see that for objects which are very probably background, which would have a probability of being an object of 0.1, 0.2, if you feed them through that loss, they still come out as small contributions to the loss, so like 0.1, 0.2. So imagine you multiply that by 100,000, because that's how many boxes you have, and it becomes a big number. You don't want that. You want the contributions from the background boxes to disappear and really focus your gradient descent and everything on the few boxes that are actually objects. So the mathematical trick that RetinaNet introduces is called the focal loss. And it's, for example, the red continuous line curve that you see here. It's basically the same as the one we had previously with a little bit more curvature. So they introduce a new gamma parameter in the classical binary cross-entropy loss to increase the curvature. And what it does is that you see now for small values of object probability, this new curve squashes them towards zero. And that's what helps you overcome the fact that you have so many background boxes predicting small values corresponding to background, and you're adding them up in one loss. And but because values towards zero are squashed, they now do not drown out the useful signal from the boxes, the anchor boxes that are predicting real objects. So small mathematical trick, but this is really key to the network actually training well. That's it. You have the full picture of how RetinaNet works. I would like to encourage you to try it. Actually, with this book, we created samples on GitHub for every single model that is described in the book. And there is a notebook that uses the RetinaNet neural network from TensorFlow Model Garden and trains it on a custom data set, here a data set of bugs. This is something that you can try yourself. This neural network actually trains, fine-tunes to be precise, in Colab on a TPU v2, so for free in just 40 minutes. And you see a couple of examples here of detections. So the ones you see, the yellow detections are predictions from the neural network, and the white outlines is the ground truth, is what it was supposed to detect. You see it's not doing too badly here after only 40 minutes of training. Thank you. That's all I wanted to share with you about RetinaNet.
Yeah, thank you, Martin. There are a couple of questions, so I'll go ahead and read them out. One is from Sahil. If we clear or remove the background of images while training, and then train our model on the images with the background removed, will it improve the model's accuracy?
Interesting question. I never tried that. First of all, clearing the background is not easy to do. Extracting foreground.
If you knew how to do that, then you're actually doing semantic segmentation in the first place.
Yeah,
right?
well,
So that itself is an ML model.
It's a full area of machine learning in itself to identify the foreground from the background. But I would think that it would probably not be that useful because my suspicion is that if you do that and then try to train a neural network on only the foreground parts with the background blacked out, then when you try to use that neural network on real images, it will start identifying lots of false detections in your backgrounds because it will never have seen actual backgrounds, and it will not have been trained to ignore anything that is not the objects that you're looking for. But well, I have never tried myself.
Okay. Second question, this is from Dave. If you wanted the bounding box size and location to be accurate to a single pixel, what would you do differently?
I have to be honest, I don't know how to do that. Let's go back to this slide here. Can you see the average precision curve? And you see that the average precision here tops out at somewhere around 0.5. So this is maybe not a very good result. What the average precision is actually some kind of average of the overlap of my predicted boxes over the ground truth. And 0.5 is not super good, but not that bad. If you push it further, you get to 0.7. But it's very hard to push it above that. So the discrepancies that you see on this slide between the predictions and the actual ground truth are actually pretty good. but you can see there are not to the pixel. There are good to maybe 10% of the size of the box, but pixel precision, I don't know, and in many cases, it might not even be a very clearly defined problem. You see here for bugs, do you include antenna in the box? Do you include legs and so on? I think pixel precision would be hard.
Awesome. Let's move on to Ryan. Maybe you can just write Martin. Yeah.
Can you hear me?
Yes.
Excellent. So yeah, next slide. So hi, I'm Ryan. I'm an AI engineer for Google Cloud, and so I'm gonna be talking about image generation. Okay, and it's a large section in the advanced end of the book. So I'm just going to cover a small portion right now. Next slide. Next, click again. Oh, why is it not putting the pictures? Oh, there they are. Can you go back one? There you go. It took a while for it to load. All right, so deep learning. So we've now seen how convolutional networks are kind of constructed. There's millions of variations after seeing a couple of them that Martin showed. And one way to do it is to, instead of having it go from the input image to some kind of classification head or some other detection kind of thing we're looking at, here instead we want to recreate the input image. Okay, so to do that, you would use an autoencoder. So before all the image deep learning work happened, there were autoencoders, and these were just dense layers, one after the other, kind of making this hourglass kind of shape, where you would have like numerical data, and you would try to recreate the numerical data, the same features on the output end. And the idea is you're trying to force the network, the weights of the network, to learn a mapping of the inputs back to themselves without it being identity, because that's useless, right? Because there's no way to then give it some different image and it to know what to do with it without it just returning it back. So what we do here is, like a lot of neural networks, we start off with a large dimensionality, and then we slowly shrink it down smaller and smaller, forcing the semantic information, the useful information that the model is going to use to survive, and the noisy information that doesn't really help us for our use case gets filtered out by this compression down into eventually, and that's through the encoder. And this typically goes down to a latent dimension. So it's some dimensionality. Obviously, if it's very large, if it's too large, then actually you haven't really shrunk much noise at all out of the system. So you're not going to have as robust of predictions. And if it's too small, now you've pinched it so tightly, now you've lost actually good information from the network. And that's not good as well. So you want to find this Goldilocks zone, this nice balance of just the right amount of dimensionality to, and this will require tuning and all that, to have just the right amount of information be passed through. So now that you have this image, like this is the number 2 right here, compressed down into this much smaller representation, you once again need to figure out a way to expand it back out. And that's where this decoder on the right comes in. The decoder is more or less they're mirror images of the encoder. Of course, they'll learn different weights than the encoder, but typically they're the same, but they don't have to be. And the idea of this is now, given this really small latent representation, how do we expand it back out into the original image? And so we're going to expand the dimensionality now. So now rather than compressing, now we're decompressing, we're expanding, and into a larger dimensional representation. Now, of course, when you first try this on your first image, it's going to be terrible, right? Putting this really good image into a network that has all randomly initialized weights, yeah, it's probably not going to be like some really ugly thing at the end, some white noise more or less, right? But through backpropagation over time, back and forth, these weights will tune themselves to be able to create the best reconstruction as it can. And this happens through the loss function. The loss function is typically some kind of error term between the pixels of the input and the pixels of the output. Sometimes it's Euclidean distance, sometimes it's Manhattan distance. There's once again, just like network architectures, there's thousands and thousands of different loss functions you can use here. But over time, eventually, it gets to learn a way to encode an image into a small representation and then blow it back up into the original image, or pretty close to it. It's never perfect, but it's pretty good. Next slide. So here's an example of that. So if we were to cut off the decoder, you could then say, okay, well, I give it all these images. Let's say it's MNIST. For those who don't remember, MNIST is that data set of all the handwritten digits 0 through 9 with like 60,000 examples, classic data set. And what we give it here is we give it all these digits, these little 28 by 28 pixel images, and it encodes it. And you can kind of look at the, if you do like a clustering of the latent representations of these things, you can kind of see, yeah, the ones in the purple there, you can see are kind of all together. The twos are together. So they all kind of bunch to get into their digit groups because they're similar looking, right? Not every 0 is exactly the same. So it's not a point, but it's close enough that they all are in the same sort of region. Okay, and next slide. Let's see if it loads the image. So there it is. All right, so you can say, well, what if I did the opposite? What if instead of chopping off the decoder and having an encoder, basically a image compressor, what if I had an image decompressor? What if I could give it random noise, some latent vectors, like -1 and 2.4, for instance, and it could create an image from that? Well, it doesn't work so well. We'll show you the next slide why not, but this would be amazing, right? It'd be amazing if you just give it, random noise and you can make images from the training. However, the noise you are giving it isn't really tuned for the problem that it learned from. Remember, in all machine learning, never forget this, a model will only do what you allow it to do. And it will exhaustively try doing that as best as it can, even at the detriment of itself. So if you give it a loss function, you give it an architecture, it will do as best it can to get that loss as low as possible, even if it ends up doing the absolute wrong things that you don't want it to do, which means your experimental design, how you actually design the loss and all that, really is important. It's completely paramount because it will actually help coax this thing along. Remember, these models are very much like newborn children or maybe like little kids, right? They really don't have any idea what they're doing. They just follow the rules, right? Hey, do that, minimize this loss. Okay, give me some numbers so I can try to minimize it. And that's all it will do. So in this case, all I told it originally to do when I had them, the encoder and decoder together was minimize the loss, make this output as close to the input as possible. But I didn't say how to do that. So it figures out some way to do it, and that's great. But as soon as I cut the system in half, now it can really no longer do the second half well because I'm not formatting my inputs to be how an encoder would do it, right? The encoder obviously comes up with some way to represent the image, right? An image, and I can't really a priori know, oh, should it be -1.0 and 2.4? Should it be -1.8 and 2.3 to get me a number 2 out? It's really hard for me to know that because I have not trained myself on learning how did this thing learn how to encode it. So there's some problems that come out about this. Next slide. So the first problem is continuity. Okay, so if it can load the image. So continuity basically means is I want 2 close points. If I sample 2 close points in in space, in parameter space, it should be very, very close together in image space. Okay, so if it loads, I can show you. So you can imagine if I took one point and then another one really close to each other, and they're close to each other in the latent space. Okay, so one is like -1 and 2.4, and another one is negative 1.2 and 2.3. So the distance between them in latent space is very, very close. The square root of each of those squared, very close. However, what ends up happening if the image would load, can you go to the next slide and maybe back, Martin? See if these things load. Oh, here we go, good. You can see what happens. In fact, you get very, very, very different images despite in image space, despite them being very close to each other. So, right, you would think, oh, well, if one's a circle, if I go just a little bit farther, it'll be not the same circle, but circle-ish, right? But you can see here, it's a triangle. So definitely not what we want. So continuity-wise, this is not good, because now if I want to make little tiny adjustments in what image is generated, I don't really know where to move, right? Do I move this direction? How far do I move? I don't really know how to get similar type images, because even the tiniest step seems to create vast differences in the generated images. All right, next slide. Oh, great, it's here. So completeness. So completeness is also another property that we want during image generation. And this is obviously when we're doing this training process, we want to kind of fill our space up as much as we can. So that way every point is meaningful. It actually creates something that we want. Okay, so for instance, here I take some random point D though, for this autoencoder, and it makes no shape. It makes some crazy thing, white noise mess, right? And this is definitely not what we want. We want it to be very uniform and smooth, our sampling space. So that way, if we choose a random point inside our latent space, in our image space, it creates an image we want. You can imagine like faces, which you've probably seen. I would obviously, if I chose any random numbers, I would want it to look like some face. I don't know what face it's going to look like, but I want it to look like a face. I don't want to randomly choose a point and get, white noise, some crazy static, screen on your broken television kind of thing, right? I don't want that. So obviously, autoencoders aren't the greatest at doing this because we didn't tell them to be. We did not give it the rules. So we just say, hey, minimize loss as much as you can between the input and output image. And so it does that, it follows directions very well, but to a fault. And we also didn't allow it, we didn't give it any more fancy machinery for it to be able to handle much harder rules, right? So we will be doing that next. Let's see the next slide, please. So this comes with variational autoencoders, okay? So variational autoencoders are a slight modification to it. And if you get into the math, it gets a lot more confusing, which we're not going to do here. But think of this now, the variational aspect of it is now we're going to be able to vary the output sequences of these things by using sampling. Maybe go back one and forward and back, see what happens. You can go forward again. Let's see if it loads the image. Next slide. Yep, there we go. Excellent. So here you can see it's very, very reminiscent to an autoencoder, except we've changed one crucial aspect. Between the encoder and the decoder, we've actually decoupled them. So no longer do we go directly to some latent representation that's fixed and is completely deterministic. So for every input image, those exact pixels, it will always have the exact same latent representation. Okay. And you can imagine, unless I have an infinite data set, which don't ever exist, I will never, ever truly be able to fill that space completely up, right? And because of my loss function, I haven't allowed it to really ever figure out some way to organize the space in a certain way that I can then use it for generation tasks. It can only really do input to output, and that's it. It can never really do anything on its own with just the decoder. So to do that, what we want to do is we want to add some randomness to all this, some variation. Okay, and what we do instead of having just a latent representation, we actually have the encoder output a mean vector and a standard deviation vector. Okay, and what these are used for is for modeling a distribution. So rather than having a fixed point, right? So you get some vector out. And remember, a vector is technically a point in that latent space. So if it's 50-dimensional, it's a 50-dimensional point, basically, is all it is. It describes some point. And that's not what we want to get the best generation. So instead, what we get is we get a mean and a standard deviation vector, which will actually be reshaped into a covariance matrix. Okay, and this now can be used to describe a Gaussian distribution, right? A normal distribution, okay, that has some mean mu and some standard deviation sigma, okay? And what we can do with that is now we can actually sample from that. And with sampling, we can have an infinite number of points we can generate from that distribution. So what actually ends up happening is this input image is actually helping train what is the mean, what is the covariance of these images that we see, of these image space, of MNIST. What is the mean, what is the covariance of MNIST? So therefore, I can then create an infinite number of different handwritten digits because I am now able to sample them rather than getting fixed points. So then when we move on to the decoder half, now we can actually sample from the distribution. And what will, it's just a normal distribution. So I have mu, I have sigma. I can then, sample a normal distribution from that, and I will now get a point, but it's not a fixed point based on the image. It's a sampled point, randomly sampled from all the images it's ever seen. And now I can pass this to the decoder, and you'll end up getting much, much better images because now you'll be able to fix the problems we had before. Next slide. So as you'll see here, the problems are now solved. Okay, so you have two close points now that now give pretty similar images, right? They're both round, circlish kind of shapes. Yeah, they're not exact because they're not directly on top of each other in latent space, but they're close enough now. It's no longer a massive jump to something way, way far away. So therefore, interpolation between points is now much easier because now we can actually say, yes, if I want to go between a circle and a square, I have those 2 points, and I know that nice little small steps between the two will get me something from starting from a circle perhaps and slowly transforming into a square. So continuity is solved. Completeness is also solved by this because now you can take a random point anywhere, and because the latent space has been regularized, it's been organized in such a way to create good images. There's really none of these punctual, really small distributions for like the number 0. It's actually much more broad, more spread out, and it fills the entire space. So you don't have these little islands. Instead, you have basically all these interlocked continents where each continent is for one of the classes, for instance. And you can see here now it actually gives, not a circle because it's not close to the circle space, but it gives in a shape that we actually would possibly want this to generate, right? Or maybe it gives the number we want to generate, or the face we want to generate, or whatever you're trying to do. Okay, so therefore we're able to solve those things, two things together. And how is this done under the hood? Well, one, besides adding those components there, once again, you need to add a little bit more because what will end up happening is it will kind of ignore the whole sampling aspect and be like, oh, okay, well, I have a distribution, and sure, it gives me this little bit noisier point, but I'm still gonna, all my loss function is shrinking the Euclidean distance between the outputs and the inputs, so I'll just go ahead and do that. And once again, it'll go, march along because that's the orders it's been given, and it won't give you very good images. But since it's a distribution, we should use some kind of distributional term in the loss to say, hey, that's great. You want to get these two things to be reconstructed very close, but I want you to do it in a distributional way. So how we do that is we add an extra term, the KL divergence, the Kullback-Lieberger divergence. And here what we're saying is, okay, I have this normal distribution that uses the mean vector and the standard deviation vector that I've learned, and I'm going to try to get it as close to a standard normal distribution, so zero mean and unit variance as I can. And we're going to try and then take these two distributions, apply that KL divergence to it to try to make the two as close to as possible. So not only now are we tuning the reconstruction, but we're also tuning the distribution representation. And therefore, now those two things combined together will give us a much, much better image generation task. That's all for now.
All right. Thanks, Ryan. So there are a few questions. Let me just read them out one by one. Question from Tolga. How do we decide on an autoencoder's architecture? Like the number of units in the dense layers or number of dense layers?
So I'll give you the easy answer. Well, I don't know which one's easier and the hard answer. Well, one answer, the simplest one, I guess, is it depends. The next answer is not that much better, and it's people usually do these things in like there's like what's the word? Common like patterns like powers of 2. So you start off with a 1024 by 1024 image. You go down to some reduction of it like 512, then you divide that by 256, that by 2, 128, down to 64, and then you're like, okay, 64 is my latent representation.
So it's pretty arbitrary, and you've got to try and see what works.
Right. So there's those things. Of course, if you play around with it and do hyperparameter tuning and all that, maybe you find out, oh, actually 64 isn't the best, 61 is. But there's so many permutations. You kind of just try, due diligence, and then you kind of stick with it and then work on other things.
Okay, question from Dave. Why is the middle layer of a GAN called the latent dimension? What's the meaning of the word latent in this context?
So remember, these are actually autoencoders and not GANs. A GAN is similar where it uses a generator and a discriminator, and then you can combine those into an autodecoder, an autoencoder architecture, which is called adversarial autoencoders. But to get to the point, what does latent mean? Latent means ideally you're looking for there's some representation under the hood of your actual data set that describes it completely, right? There's some kind of way that we can minimize, shrink down some really high dimensionality down to some lower manifold, down to some lower form. And that's what there's some underlying, that's what latent means. There's an underlying aspect to your data, and that's what you're trying to do, is you're trying to take this large image, squeeze it down, get rid of all the bad stuff, keep all the good stuff, and then blow it back up into the original, so that way you learn some smaller version of how to get to it, right? Like I said, the encoder is pretty much an image compressor.
Okay. And finally, a question for you, Martin, from NetNail. If we had multiple objects on the foreground and wanted to detect all of them, would this architecture work? And if we want to identify only one object from all the objects in the foreground, what would change?
So yes, the RetinaNet architecture works for identifying multiple objects. If you remember when we had this image of how you encode your ground truth boxes. So I said at the time that you drop one ground truth box onto this sea of anchors and identify the one match. This obviously also works if you drop 5 different ground truth boxes and identify 5 different matches by biggest overlap. There is the fact that I used 1 was just an example, just to simplify it. This works with any number of ground truth boxes in the image.
Yeah, in fact, your example image showed 2 butterflies, for example.
And yes, indeed. So the example image showed 2 butterflies here. And as you can see on the sample that you can try yourself, there is an image with two spiders, and it correctly identifies those two spiders.
And to identify only one object, you would label only the objects that you care about, and then probably pick the one with the maximum probability.
Yes, exactly. So actually what is going on behind the scenes, one topic I did not mention is that you remember that you pick, for example, here 5 different levels in the backbone from which you extract feature maps and then apply detection heads to those feature maps. So each one of them will be detecting all of the objects in the picture, and you'll end up with plenty of detections for the same object. So there is one part that I didn't mention. It's there is an algorithm that takes all the overlapping detections of the same object and tries to find only one box there. So that is also going on here. Now, if you wanted to optimize something for expressly detecting a single object in every image, well, I guess you could use the exact same architecture and just encode this in the ground truth of your training data. Would there be a way of, well, the simplest way I can think of is just to take a way of encoding this in the architecture of the network itself would be at the end to pick the box that has the highest object probability. That would be the
which is exactly what we do when we do a softmax, for example, in classification.
Yes.
Cool. So let's move on to the last section. Like Martin talked about like a backbone architecture and how to use those backbone architectures to solve a problem. Ryan talked about like an advanced use case, generative adversarial networks or GANs. What I will do, like the final part of the book also looks at specific computer vision use cases and says, like, if you're going to be solving this specific problem, here is a trick that you want to be aware of. This is something that you want to be able to do. So next slide. So let's say, for example, you are eBay and you want to basically implement image search. So for those of you who've used eBay, like, you know, when you say, I'm going to go sell my camera, you basically take a photograph of your camera, you upload it onto the eBay site. And when you do that, eBay behind the scenes searches for a match of the thing that you just uploaded with all of their images on their entire product catalog in the back. They do an image search and they basically surface out, oh, it looks like you're selling a Nikon X300 or whatever. And these are the like recent 5 auctions involving this camera. Do you just want to copy all of the descriptions and the price, etc., from those? Like, when you think about it, what are they doing? They're basically taking this one image that you uploaded and searching against their millions of images on the background. So this involves 2 things. One is how to compute whether 2 images are similar, right? You can't just go compute an Euclidean distance between the images, because obviously the image that you took, the photograph you took, is not going to match in terms of background, etc., the image that they have in their catalog, right? In the product database. Once they have an image search, they also basically support another use case, which is to find it on eBay. Like if you see somebody wearing a pretty neat shirt, you can take a picture of that shirt and say, find this on eBay, right? Or you see somebody reading a book, and you can take a picture of the book and say, find this book on eBay, right? So that also takes advantage of image search. So, but from our computer vision standpoint, the question is, how do we implement image search? Next slide. So if we were to be pretty naive about it, right? And let's wait for the image to load. If we were to be pretty naive about it, what we would do is that we would take all of our images and pass them through a pre-trained model. Let's say we pass it through a mobile net or an efficient net, all of these, because they want to allow you to do transfer learning, they basically have an ability to basically spit out the embedding layer, right? The layer that you actually attach your classification head to. So you can take those embeddings and you say this embedding is a latent representation of the image itself, because obviously it had enough information for you to be able to classify the image. And so it already extracts the most important aspect of the image. So this is why you don't use an autoencoder here, because you don't want all of the information in the image. You want the most important aspects of the image. And your pre-trained embeddings are already trained to basically do that. Your image classification, you use it for image classification. So it must have all of the data. So you say, I'll go ahead and create all of the pre-trained embeddings, and then I will compute a Euclidean distance between the embedding of the image that I just uploaded and the image I have in my product catalog. Right? That's just a vector distance. You can do that. But again, when you're going to do that, if you are basically going to upload an image and on the background, you basically have 300 million images, you don't want to go around and compute 300 million vector distances. That's going to take too long. So you want to prune the search space and make it a faster search. And so there are search algorithms out there. So you might say, let me go use Scan, which is basically an open source library that allows me to basically go ahead and do the search. So that looks great. And from the point of view of writing the code, it is very, very, very straightforward. So you basically go ahead and you create a Keras layer that basically creates the embedding, and then you call predict with that model that only produces the embedding layer, and then you basically load that up into the Scan, which is an indexer. And then whenever you want to do a search, you say, go ahead and search. So 4 API calls and you're pretty much done. It looks super easy. So you want to do a search, and if you knew nothing else, this is what you would do, because you've read the book so far and you know about image embeddings and you know about, and hopefully you know about searches. So you say, okay, this is what I do. Next, click. Unfortunately, though, this is not going to work. And the reason it's not going to work is if you look at the example, if you just click backward, Martin. Okay. If you look at the examples, right? So you basically you're searching for an image of these flowers, and look at what the closest image is. It just happens to be some arbitrary arrangement of things that is not even a flower, right? It's not even a flower, but it has that arbitrary arrangement, and it says, okay, this must be the thing that is closest. It's ridiculous. And the distances are also enormous, right? And so this doesn't really work, right? This idea of let me just go ahead and do the embedding and do a vector distance and search on the vector distance sounds like it's a neat idea, but it's not going to work. So if you want to image search, what do you do? Next slide. Okay. What you do is that you use what's called a triplet loss. Okay. The idea behind a triplet loss is that in every batch that you're basically training your model on, you basically pick the particular anchor point, the particular row for which you want to compute the loss, and you find within that batch itself, you find a positive example and a negative example. A positive example is something that has the same label as this thing that you want to compute the loss for. And a negative example is something that has a different label. So it's often also called a contrastive loss. So you contrast and you basically compute the loss. And what that loss function does is that it weights the loss in such a way that you want the loss to be, the distance to be smaller for objects with the same label, for images with the same label, and the distance to be larger for images with different labels. So not only do you use the embeddings, yeah, you could, but you actually train those embed the losses to create those embeddings in such a way that the embeddings, the distances are small for images with the same label and are large for images with different labels, and the embeddings themselves capture the information in the image. Once you do that and you go ahead and then you look at the embeddings that you got, if you look at it, like say TensorBoard, for example, you will find that all the roses are all clustered together, all the dandelions are clustered together, etc. So now your embeddings are in such a way that you can actually use them to compute a distance. So just as one simple trick, which is when you train your ML model, and if you're going to be doing it for image search, what you want to do is that you want your loss function not to be cross entropy. You don't want it to be mean square error. You want it to be a triplet loss. And it's already available in TensorFlow, and it's available in Keras. So just put that loss function in, but you have to be aware that these exist, and this is why you use them. Next slide. Okay. And with that, we basically move on to, like, if you have any questions specifically for me, otherwise we can just do a very general Q&A.
Great, thanks. So just quickly remind, you can post, for the folks who have questions, you can post in the chat. And when you type in the chat, make sure select to everyone so we all can see the messages. Again, if you prefer to speak, ask questions, just raise your hand, we can unmute you.
So there is one question in the Q&A that we missed, and that was if for object detection, it was useful to shift your images to black and white rather than color. Well, I think that modern neural networks can handle black and white and color pretty much automatically. That's what's nice about convolutional networks, is that if the color information is not useful, it will be discarded automatically. And that's why I would not really advise shifting the images to black and white yourself, because if the color information turns out to be useful, for example, in wildlife, a lot of background is green, and that might be a useful, signal that the neural network picks up. Then discarding color might not be so useful. In this case, really, I would let the network do the work and decide whether the color information is useful or not. Oh, good question. Is there any way I can get in touch with the speakers? Yes, we all shared our Twitter handles in the very first slide. Let me put that back on the screen. And yes, please reach out on Twitter with questions. Absolutely. And yes, thank you, Lak, for putting the Twitter handles there. I think there is one more question about predictions. Can the false prediction be removed in RetinaNet with the help of extra group with the images of all not related to detection group? I'm not sure I understand this question. Lack of Ryan.
Yeah. I think what he's asking is, now suppose you're trying to find 3 types of flowers, and you only care about the 3 types, but RetinaNet is finding other objects and categorizing them as one of these 3 types because that's what you trained it on. Would it help to create an other category consisting of objects that aren't not these 3 flowers that you care about, but are also flowers?
Oh, okay, I get it. So it's, yeah, I think it's definitely worth a try. Definitely worth a try if you have different flowers that have white petals and a yellow center and look very similar. And you have the network confused about them. what you're saying actually is that you are going to not just add the category, but you will have to add a data set, a labeled data set that has those two flowers that look very similar, that are labeled differently. And in doing that, you're providing the useful information to the neural network for helping it to differentiate between those two very closely related flowers. So as always in machine learning, the answer is more data.
And also try it and see. Okay, so talking about more data, we have a question from JP Bianchi. I've seen in some recent papers that vision transformers have now outperformed CNNs. What do you think? Well, we do have a section in the book on vision transformers, and we basically talk about what they are and how to use them. There is a sample of a vision transformer in the Git repository for you to try out. But JP, what you've got to know, you should look at those papers and look carefully at the size of the data that they're using to train their ML models on. Vision transformers today work only when you have in the, close to 100 million images or so, right? It doesn't work on your standard garden vanilla smaller data sets. So the title of our book is Practical Machine Learning. And so most of the book, that's why we focus on CNNs. Vision transformers today are for those very, like a handful of use cases where you have tremendously large data sets.
There was one more question, Lack, from Dave. In what situation would scan work?
In what situation would scan work? Oh, I should be very clear. Scan totally works. I use scan for both my pre-trained embedding and for my triplet loss embedding. Scan is the search index capability, right? So you definitely do not want to go around computing the Euclidean distance for all of your entire data set for every query. So you want to do search space pruning, and that's what scan does. The difference between the two approaches I talked about is, do you use a pre-trained embedding, or do you customize that embedding with a triplet loss? And my answer is, your pre-trained embedding is not set up in such a way that similar images have similar embeddings. We think they are, but they're not, right? Similar images do not have similar embeddings, and we need to force them to have similar embeddings, and that's why you train them with the triplet loss. I hope that clarifies. In both cases, we're going to use scan. It's the question of what embedding do we use to do the search and the distance computation.
And maybe I can add that there might be very different definitions of similar. What is similar? Two images can be similar because they are all yellow objects on a black background, even if one is a flower and the other one is a shirt. And what you do with the triplet loss is you communicate to the neural network what similarities you actually care about. Because in that triplet loss, you define pairs of objects that you consider as being similar, a yellow flower and another.
The most important thing is that in the triplet loss, it takes into account the label, where the embedding, it's hand wavy on what the label is, because it's pre-trained on the ImageNet labels, which may have nothing to do with your own labels. Cool. Awesome.
So is this just for the questions for the recording about the webinars? Yes, the session is recorded. You can watch the recordings on the AI Camp YouTube channel. Just search the AI Camp on the YouTube. You also can go to the website. They have a link. Go to there to watch directly after the event is done.
Okay, last question. For the constant environment like industry, don't you think black and white is better way to train? In general, you want to train on the exact same kind of images you will see in prediction. So if your production system is going to do black and white, you want to train on black and white. So that has nothing to do with black and white or not. You want to train on the same kind of images. If your production images are low light images, your training images have to be collected in low light as well, right? So that's pretty much the great idea. And all right. Do we want to answer like 2 more questions that come up, or like we should close? Oh no, actually we're running out of time. JP, sorry, we're running out of time here. So
no problem. Let's finish the questions. I think we have a few more questions.
Very interesting question. Are there models that are able to build a hierarchical information structure like we humans use? So for example, a bird is an assembly of feathers, beak, wings, and so on, each of them being made of smaller objects and so on. Is there a way to extract this type of information structure from a data set, store it, reuse it later? So first of all, I'm not sure that we as humans, when we perceive something with our visual cortex, we actually organize objects in this type of hierarchical structure. We don't know exactly how our visual cortex works. There is some of that, but I think that when you write the sentence, a bird is a collection of feathers and so on, what is working in your brain is your the part of your brain that is wired for language, more than the part of your brain that is wired for vision. Now, a convolutional neural network actually does create some of that hierarchy. A convolutional neural network does break the image into small feature first, like edges and corners and textures and so on, then assembles those through additional convolutional layers into small recognizable features like feathers, beaks, and so on, then assembles those into a whole bird. So that is there. And there are examples on the web of visualizations of what those individual neural network convolutional layers actually encode, actually see. And you can see all of these features. You can see the textures higher up. You can see the eyes, for example, in the middle, and you can see the full dogs and birds down at the bottom. Now, you ask a very good question, which is about retrieving that information and understanding how a neural network has encoded a bird as a composition of semantic concepts. That's much more difficult to do. That's an active area of research. Basically, it's part of explainability, trying to understand how a neural network does the work that it does. But at the basic level, a neural network is really a black box. You put in an image and out comes a classification for if it's a classification network. And you can try to peek inside, and there are research going on that, but it's not something that is very practical to do, unfortunately. That's one of the weaknesses of neural networks. Another one about detection. Does edge detection, can edge detection be used as a training data set if you are not bothered about the color of the object? So if you use edge detection as a training data set, what you are going to train your neural network to do is to detect edges. I'm not sure exactly what it is you're trying to achieve here. If you want to build an edge detector, there are actually non-neural network methods for doing that work very well. So I wouldn't do that. If the question here was whether it would be useful to pre-treat all of your images with an edge detector and feed only the edges to your neural network for object detection, Again, this looks like feature engineering that you do by hand. So feature engineering, I mean, hand feature engineering, selecting features that you then feed through some machine learning algorithm, used to be a big thing in machine learning. Nowadays, it's much less of a big thing because the neural networks have enough expressivity to figure out the best features themselves. And for something like edges, they're actually quite good at it. Convolutional layers can very easily be trained to become edge detectors. So a convolutional neural network, if edges have semantic significance in your image, it will train by itself an edge detector and then use that. Now, I'm not saying that all of possible features can be figured out by a neural network automatically. I can give you two examples which are hard for a neural network. For example, doing a Fourier transform on sound or even images. A Fourier transform to go from time space to frequency space is a fairly complex thing, and a neural network is not very good at doing that. So if you think that is that the information of your data set is much more visible in frequency space, there it might be useful to transform yourself, your data in frequency space, and feed that to the neural network.